We definitely understand the dual of the problem. Actually, it has some beautiful geometrical interpretations of what the dual can tell you. That in the simplest, shortest path problem, the dual solution, the dual variables for the flow constraints actually are the cost to go to the on the graph. And there's a generalization of that we can see in the dual of this problem, which is like a small cost to go function. When the convex relaxation, the dual reveals like the cost to go structure on the sets, which is it's beautiful and good. The instances where the convex relaxation is not tight, we understand some of the properties of a graph that can cause that. Like the one that we use to do a reduction to NP hardness is when a bunch of cells are all overlapping and you can just walk around inside the cells without having to visit them. There's a couple of cases like that where things are perfectly in symmetry and you could really, but they're quirky examples. And so we understand those by having a handful of examples. I don't think we can say as much about them. I mean, we do have the primal dual solution. We can tell that there's an optimality gap, so we can identify when they happen, but we haven't thought more about, they seem quirky, and we haven't thought more about how to make those particularly better. Oh, sorry, I'll let the microphone people.
Okay. Yeah, so
oh, great.
Right so yeah, I have two questions. The first one is actually related to the last question. So you were mentioning that writing these constraints is difficult. So you mentioned that you missed some constraints and then Pablo was like, oh, you're missing a constraint. So I was wondering how difficult is it to write these constraints? If you come up with these convex regions, write the natural flow constraints, is that sufficient, or like are there things that like you got to be smart about how you're writing?
That's awesome. I'm super glad you asked that. So it is true that Pablo caught us and we had to add another constraint, but there's some sense in which though that I think you'd ask him, like, are you going to find another constraint? He'd say, no, we found them all. Like you can add generalization on the graph of convex sort of problem, but there's some sense in which we've kind of found them all, and that work is done. There's a chance you could make it better if you wanted to do something else, but that is carefully studied, well understood. Book is sort of closed. For the motion planning formulation, now we have this question of how do you encode trajectories in these sets? There's many decisions to make there. We made a particular set of decisions. I think that book is way open. We've got an initial version that was convinced us that this is important and impressive, but I think there's a lot more decisions about what constraints to add there. But once you cast it into the graph of convex, however you turned it into the graph of convex sets, then the machinery takes over, and that's pretty mature at this point.
So the kind of cases where you don't have this tightness, those are not due to, like right now, like the quirky cases you were mentioning for the last question, those are not due to like not having like the right constraints.
Correct. I think there is NP hardness. We will not have a convex relaxation that's tight in all cases. I think. I mean, you can add exponential numbers of constraints to get back up there, but if we limit the class of constraints, then this is, I think, the sweet spot of constraints that we've added.
And just another second quick question. So
yeah,
you mentioned the dynamic obstacles case, and you mentioned you guys are working on that. Can you just tell us a little bit about like how you're approaching that case?
Yeah, of course. So, I mean, if I were to take a PRM that I do a lot of pre-computation, and then I would suddenly insert some obstacles, then you could imagine, comparable to trimming edges that are now in collision, but leaving my graph around, I could shrink regions that are now in collision and continue to plan. There's a lot of things like that. I think a lot of the tricks that you would use in a roadmap, we could apply similar tricks here. There might be some things fundamentally better. We're taking some cracks at it, but that's the first thing I would try to do. Yeah.
So can you say a few things about how you represent the convex sets in the general configuration spaces, including non-Euclidean, and what kind of operations do you need online as post-containment in that set?
Yes, good. So in general, we want to find polytopes in Q, my joint angles. So Euclidean or non-Euclidean, I'm just going to write a polytopes, linearly, half plane parameterized polytopes in Q. For the sums of squares version, the sums of squares likes polynomials. Sines and cosines in Q are not as fun to deal with. There's a handful of ways you can transform those variables into polynomial coordinates. The one we did in the paper you'll hear on Friday, I hope, is by taking the stereographic projection. So you end up having polytopes in the tangent of Q, roughly space of tangent of Q over 2 kind of space. But it's basically polytopes in Q. And you're right that, so at runtime, the graph of convex sets parameterization does the work for you, right? So it's actually constraining the B-spline to live inside that polytope by putting convex constraints on the control points of the B-spline inside a polytope, or any convex set, but inside a polytope. And so I think, what's your runtime concern in that regard?
Yeah, like what kind of operations then do you need during the online to interact with these elements? But the way I understand it, you have done all of the hard work, right? So now we can be naive users of the representation that you have built.
I hope I hope some people will use it right out of the box. I hope some people will push it forward. But yeah, I think once you have the regions, which is an offline computation, the online computation really is just solving these convex problems. It should give you Q trajectories that you can just go and execute, right? If you have acceleration jerk constraints, those are coming soon, and effector constraints, we know how to approach that. Those are coming soon, but those are all, I think, can fit in the toolbox. Thank you. Yeah.
I think we'll have to unfortunately wrap it up there, but let's thank the speaker again. Okay, everybody, coffee break. Coffee is outside. We reconvene here at 11:15. Sorry about the CCL thing.
No. It was just because of us. I was like, what?
I had it written down, and then
it doesn't matter at all. No,
yeah.
That's great. Anyway, it's great.
What happens is, to make it complete, this axis is the design of the blocks, using fields or whatever, and then this axis is the execution process. You add a wheel that doesn't do anything when you really do that clock. So you pay extra on the one dimension, but it's yeah.
So there's yes.
When you have permission, all of no matter what. So it's like a key norm. mean, it's an infinity dual, so it's like a relationship power, very high power. Zero gravity from it, yeah. Should we grab some?
Yeah.